Hey guys, back with another video. In this one we will learn about the complementary error function and how we can use that to solve linear equations. I will define it. It is denoted by ERFC of x, and that is complementary error function is equal to 2 over the square root of pi times the integral from x to infinity of e to the minus t squared dt. Now recall that this is a function of x rather than of t. So once again, we are evaluating the area under e to the minus t squared from the value that we choose x to infinity, and then multiplying all of that by 2 over the square root of pi. Let's look at the exact same example from last time, except we will choose a different initial condition. So we have dy dx is equal to 2xy plus 1. And I said initial condition. Actually, it's going to be a boundary condition here, our end boundary. We will have the limit as x goes to infinity of y is equal to e to the x squared. A little bit different condition that we must satisfy, but it will make sense in the end. So I will go pretty quickly through this since we already covered this example. I'll just write out the steps. Minus 2xy equals 1. We know that our p of x is equal to minus 2x. Once again, if you haven't watched my first video on linear equations, I would strongly suggest watching that video so you can understand the technique of finding an integrating factor. So we integrate this, we get minus x squared, which means that mu of x is equal to e to the minus x squared. Now, per the formula, we have d dx of e to the minus x squared times y is, and then this is equal to, and I'm leaving space here for my dx, this is equal to e to the minus x squared times our right-hand side, which is just 1. If we take the integral of both sides with respect to x, then we will realize once again that we have no analytical way of solving the right-hand side of this equation, which means that we will want to not do the indefinite integral, but rather the definite integral. So we will have the integral from, and let's look at our initial condition, or rather our boundary condition here. And we see that we have an infinity. And the error function was 0 to x, and the complementary error function is x to infinity. So it makes sense that at least one of our bounds here should be infinity, and that would mean that we would end up using the error function. So let's evaluate from x to infinity of, and we will change our x's to t's, but as long as we stay consistent, it won't change the value of anything. Recall once again, this is a function of t, y is a function of t, dt, and this is equal to the integral from x to infinity. Our bounds must be the same on both sides, e to the minus, and this is not x, this is minus t squared dt. Well, the d dt and the dt cancel, and what we get left with is we get e to the minus t squared times y, and this is being evaluated from x to infinity, and this is equal to, well, we can do the same method as before. We do square root of pi over 2 times 2 over root pi. That cancels out to be 1, and then we multiply it by x, the integral from x to infinity of e to the minus t squared dt. Now remember, when we solve improper integrals here, where one of the bounds leads to an infinite value, then we need to write it as a limit. So we will say that the limit as b goes to infinity of e to the minus t squared times y of b, we will replace infinity there with b of x, and this is equal to, we get the root pi over 2 times, and this on the right hand side is equal to our complementary error function. So we will write the complementary error function, ERFC of x. Now, if we plug in our bounds, what we get is we get the limit as b goes to infinity of e to the minus b squared times y of b. And then this will be minus, and the next term won't have b in it, so we don't need to continue the limit. So this limit will be contained within the brackets. This will be minus e to the minus x squared times y. This is equal to root pi over 2 times the error function, the complementary error function of x. If we look at our condition above, we know that when we take the limit of some value, or of some variable, in this case x, to infinity of y of whatever that variable is, then that will equal e to whatever that variable is squared. So here, since we have a b instead of an x, we know that the limit of as b goes to infinity of y of b will equal e to the b squared. It's exactly what we had written up here, and I will put a square around that. Which means, and we know that when we have two functions that are being multiplied by each other within a limit, we evaluate both of them and we multiply those by each other. So what we get is we get the limit as b goes to infinity of e to the minus b squared, and y of b here would just equal e to the b squared. This is minus e to the minus x squared times y is equal to root pi over 2 times the complementary error function of x. E to the minus b squared times e to the b squared, the two exponents add up to 0, e to the 0 is 1, and then the limit as b goes to infinity of 1 is just 1. So we get 1 minus e to the minus x squared y is equal to the square root of pi over 2 times the error function, the complementary error function. And once again, I didn't write that up there, of x. Now to solve for y, we can add this term over and we could subtract this term. So what we get is we get e to the minus x squared y is equal to 1 minus root pi over 2 times the complementary error function of x. Now multiplying both sides by e to the x squared and e to the x squared on this side, we get y is equal to e to the x squared times 1 minus the square root of pi over 2 times the complementary error function of x. And that is the solution to our differential equation with the condition that we included. Well, I hope you found this video helpful. If you have any questions, please leave a comment below. I will be including more videos on linear equations and on the error function and complementary error function. So look forward to those, and I will see you in the next video.